Good morning again, Joseph Park, chairing the e-poster session for Sensors T3.1. Thank you for joining us this morning. It seems that we have fewer presenters than were registered, so we may have a little bit more time for questions at the end. I invite you to enable your video so that the other presenters and attendees can see you. Please remain muted while you're not presenting. Again, we do not allow any videos to be streamed, but you are able to share a slide or two if you like. And I would like to start off with Michael Fox, and then secondly, go into Sylvain Topin. So Michael, I give you the floor for 2 minutes. Thank you. I'm not hearing anything, Michael.
You. It was double muted, like
there we go. Now
the usual. Thanks. My name is Michael Fox. I'm going to talk a little bit about the development we have at PNL on a high-resolution beta gamma detector for the beta detector. We are aiming to replace the plastic scintillator with a silicon beta cell. And so that goal for that is we want to be able to improve our resolution over the plastic scintillator. So from about 30% for the plastic to about 10% of the silicon or better. And with that, improve our isotopic discrimination, being able to better discriminate 133M and 131M from 133. We're able to then improve our sensitivity. So you can see here on the right is a quick overview or schematic of the detector. If I go to the next slide, you'll see just a little bit about the detector. So the beta cell is here on the left-hand side. Some of our laboratory setup is here on the right. And if we use this for the initial testing, we've calibrated the beta cell to see how it performs relative to plastic. And if we go to the next slide here, this is kind of the main point where we can see what's the impact of the silicon. And so these are for the two metastable isotopes. On the right-hand side, we have silicon. Left-hand side, we have plastic. We don't show the 133M and 133 and 135. With the betas, there's not a huge improvement there, but the conversion electrons really benefit from the improved resolution. And so you can see the peak circled here on the right-hand side for the silicon is much better. They're much more visible compared to the 133 background. And so that's where, with the improved resolution, we're able to then have better isotopic discrimination. And I have a few more slides that if you come to a poster, you'll see for the stability of the detector and how it performs over a long period of time. But overall, it's performing well. It's a good improved resolution detector, improved isotopic discrimination and memory effect. And we've got some analysis updates and electronic updates to still perform though. So come to my poster and you'll see a little more about this information. Thank you.
Cool. Very nice. We'll next go to Sylvain Topin and then follow with Manish Sharma. So Sylvain, you have the floor.
Morning. I cannot share my screen, unfortunately. Just a few words about my poster. It is going through the history of the noble gas development at CA from SPALAX and SPALAX new generation system with beta gamma high resolution systems, the PIPS box development, and more recently the pixel box development, which are silicon pin detector in coincidence with gamma detector. And also development on silver zeolite adsorbent. And I can also give the opportunity to see the file of my colleagues, Antoine Cagnan, Olivier Delon, and Axel Gourg on this subject more in detail. Thank you.
Thank you. Next, Manish Sharma, followed by John Merchant. So Manish, please. And no audio yet. we see your slide, but
Hear me now? Sorry about that.
there we go. There you are.
So yeah, I'm Manish Sharma. I'm a postdoc research associate at Pacific Northwest National Laboratory in the United States. My work is about how we can improvise the sensitivity of radionuclide monitoring system at IMS stations. I will specifically be covering my slide 5, 6, and 10, just in case if you want to go offline and if there is any issue in the transitions. So the radionuclide aerosol sampler and analyzer, also called RASA, was first designed and developed by us, PNNL, after about 6 years of research and development. The picture is here. Basically, the air comes from the top. The radionuclides of interest are deposited onto an air filter, which gets analyzed in the HPG detector, as you can see here. So the idea here was just to develop a next generation design of the RASA by including one more detector, because that improves the efficiency, the sensitivity, and also operational resiliency, because you can count on one detector if the other detector fails by any chance. So to demonstrate this concept, we developed a prototype here at PNNL, as you can see on the right here. It was developed in March 2021, this year. You have 2 detectors instead of 1, as you can see here in the schematic as well, facing up and down, and then you have the sample in the between of 2 detectors. So I'll just go to the main highlight of my work. By this prototype, we basically demonstrated that the sensitivity improved by about 30% on average for CTBT relevant radionuclides. This top right picture is what I was talking about. The efficiency by the addition of detector basically improved by up to 200%, as you can see here. Similarly, we compared our results with the real RASA that is already installed at 22 IMS stations. As you can see here, the picture in the bottom, you will see that the summed spectra, which is the combined detector output, is basically better than the singles. So that's the crux of my presentation. Thanks.
Thank you. Thank you. Appreciate it. We can next go to John Merchant, followed by Haoyang Lee up next. So John?
Okay, thank you. Let me pull up my slides. Can you see them?
Yes.
Okay, great, thank you. My name is John Merchant at Sandia Labs. We've been performing some evaluation of the Hyperion infrasound sensor, recently approved for use within the IMS. And we worked most recently to develop guidance for station operators to help them ensure that the infrasound stations are meeting the minimum noise requirements for system noise during station revalidation. And so we performed a series of tests to answer a set of questions about what steps the station operators need to take when the sensors are first set up, if there are power cycles, and if the sensors are not equilibrated properly to the temperature environment in which they're in. Let me just show one slide with some of the results when we were doing testing in which the sensors were soaked at a range of temperatures from -36°C up to +30°C. And then we placed them in an isolation chamber and monitored the evolution of their system noise over time. And we found that the sensors frequently needed as much as 12 to 16 hours of time in order to reach equilibrium. Anyway, there's a lot more results in here. Hopefully others might find these interesting to help them learn best how to set up the sensors for proper use within the IMS. And thank you.
Thank you. Appreciate it. Next, Haoyang Lee, and we'll follow with Clement Benovich. Thank you, Benovich. Haoyang?
Okay, I will share my screen. Can you see my screen? Hello, everyone. This is.
You could try turning off your video. Yes, we're losing your signal, so the audio is not good.
Can you see my screen now?
We're also losing your audio, so perhaps you can just disable the screen and just give us an audio presentation.
Can you hear me? Excuse me?
I'm afraid we're still not getting the audio.
Excuse me, don't hear me?
There we go. This is better.
Can you hear me?
Yes.
Can you hear me now?
Yes. Yes. Now it's better.
I
Yes.
will share
Yes, I'm afraid
my
we're unable to get a coherent audio stream. So let us come back to you.
Oh.
I will let's move on to Clement Bednarix, and we'll come back to you at the end and see if we can get a better signal. So so stand by, and we'll move on to Clement. Thank you.
Hey everybody, I hope you can hear me. I am Clement Benovich from Environs. And I'm starting, whoa. Can everyone see my screen?
Not yet. There's no image. We can see the mouse moving around.
Okay.
Just on the phone.
Maybe try again.
Yes, we're still not seeing any video, so you can perhaps switch your source.
No, it's sharing the screen. Okay, should check.
Anyway, I will do without PowerPoint, and I will share my PowerPoint later on. I mean, for the roundtable, right? So,
Okay.
hey everybody, my name is Clement Benovich. I work from Environs company, company that design wind noise reduction system for infrasound sensor. My presentation here is focusing on two main techniques related to wind noise reduction system, and that allows the end user of an infrasound station to verify the performance of its wind noise reduction system. The first technique is the pressure test, and the second technique is the use of reference system signal comparison. So in the first part of my poster, I introduced the design we made with the help of CTBTO of inlet ports with valves, bringing easier implementation of your pressure testing process. And then I develop and explain the main steps of the wind noise reduction system pressure testing using this valves item. And in the second part of my presentation, I mean, I will present some results showing some leak effects simulated on the wind noise reduction system, and explain how it can effectively affect your wind noise reduction system capabilities. And on the second part, the second technique I develop tackles the concept of using a reference sensor and system, and I will show how we can move forward on a signal comparison between a sensor connected to a reference inlet port and a sensor connected to a wind noise reduction system. And I will emphasize the interesting correlation and assets of such signal comparison within a same array element. So yeah, if you want to know more about such wind noise reduction system performance verification technique, please join the roundtable and ask some more questions. Thanks a lot.
Thank you. Yes, we'll do that. I'm interested in that. Next, we can go to Christoph Gaby, followed by Matthew Godin. So Christoph?
Yes, hello. So let me share my screen. So normally you should be able to see my screen, and I hope you can also hear me.
Yes. Yes.
So yeah, thank you. Hello, I am Christophe Geff from the Belgian Nuclear Research Center. So in this poster titled Study of Materials for Improved Adsorption of Xenon at IMS Radionuclide Stations, we present the results of a project, an EU-funded project in support of the CTBTO, where we looked at a new type of adsorbent material called metallic organic frameworks, because these materials have been recently they have shown promising xenon-krypton separation. So we wanted to know if these properties could also be of interest for IMS noble gas systems, for xenon collection and purification. And for this, we also compare these materials to the materials which are currently used in IMS noble gas systems, so activated carbon and silver exchanged zeolites. And for this, we compared, we investigated three aspects. The first one is the collection of xenon from air, so the amount of xenon that can be retained in the material. And then their ability to separate xenon from other gaseous components in the air. And last but not least, the durability of the materials against adsorption-desorption cycles. So I invite you to come to see the poster, and I will be there to answer questions if you have. Thank you.
Thank you. And we can go next with Matthew Goodwin.
Good morning, can you hear me?
Yes, very well.
Great, I'm just going to share my screen. Hopefully something's appeared. So this is a poster on the measurement of some gaseous fission products using a coincidence electron-photon or beta-gamma detector. So we produced some fission products using a highly enriched uranium target at the National Physical Laboratory near London. And then we extracted the gases that were produced at 2 points in time for measurements. We were able to compare these measurements with some simulations. We detected what we expected, which was radioxenon isotopes 133, 135, 133M, 135M, and some radiokrypton isotopes as well. So the sort of system that we use the Miriam links detectors for one links for each detector channel. We used the Miriam and CEA developed PIPS box and two Ortec high purity germanium detectors. We acquired everything in list mode and then sorted it using C++ and root. Some of the results that we've obtained are shown here. So you can see some beta gamma coincidence spectra in high resolution. We've pulled out some of the key signatures. We've picked up on some signatures that we haven't noticed before, given the activity ratios that we've seen. And we put the projections here. Some conclusions here, and we've also got a talk on this similar system in the session 3.2. I'll be happy to take any questions that you have. Thank you.
Thank you, appreciate it. So I have on my screen someone logged in as D3K115, which I believe is James Hayes. So James, is that you, D3K?
That is correct.
You have the floor for 2 minutes. Thank you.
Okay. See if I can get this to share.
Yes, we can hear you, but.
Okay, can you see my screen now?
Yes.
Okay, so my name is Jim Hayes from Pacific Northwest National Laboratory, and I'm going to talk about Xenon International today, give you an update. Xenon International is the next generation radio Xenon system that is in preparation for a I'll say preparation for use in the IMS. It is a high throughput system, 6-hour collection cycle, much higher sensitivity than the current IMS systems. It is currently going through an acceptance test for the PTS, and the acceptance test will determine if the system can be used in the IMS. The system just completed 6 months of testing at Teledyne Brown Engineering and is currently just about to start phase 2 at Shallon's Land. Go through a little bit of the results in this poster, so if you want to get more details, just come visit. Let's see if I can advance the screen. So the system, it is designed for 7 regions of interest and uses the 7 regions shown on the left. The 4 isotopes that we measure are the 131M, 133M, 135M, and 133. However, we did see lots of unexpected radioxenon, and you can see James Ely's talk. He's already given it. These pictures show some interference with Xenon 135, Xenon 125, interference of 125 with 133, 135, 131M. These are different than what James shows. He has pure isotopes. This rate of interest is of interest because these isotopes interfere with those analysis routines. Spikes were processed and analyzed on Xenon International. They were sent to the UK for analysis, confirmatory analysis. The PTS did not have a 7 region of interest analysis. They developed that just recently. We compare the Xenon International with Autostrada 7 ROI for all 4 isotopes. Got uptime of 98.4%, and we've completed quite a bit of documentation necessary for phase 2 in Shallon's Land. We've updated some software, and we've installed new coded beta cells in the system that is in Shallon's Land. The system started up actually yesterday, and the training will be conducted by Teledyne Brown to DFS, who will be the operators of the system. This weekend, we'll start the 3-day detector background, and if all goes well, next week we'll start phase 2 testing of the acceptance test of Xenon International. And if you want any more information, come to the poster, and happy to chat.
Thank you, Jim. Appreciate it. So I believe we've covered everyone who has logged in and was pre-registered. So I think we can.
What about Judah?
There is someone logged in under the name JUDAH. However, I don't know who that is, and I'm reticent to just give the floor to someone who I don't know who they are. So if you could send a message, if you're actually a presenter, and identify yourself.
Judah Friesen. He said he's Judah Friesen.
This is, I don't see him on the list.
He's not on the list.
Yeah, he's not a registered presenter, so.
Maybe ask him. Okay, in the meantime, you can give.
So Judah, if you'd like to send a message to identify yourself, we can ascertain whether or not you're one of the registered participants.
Oh, yes, he says P31187. Poster.
And what's his name? Okay, so then let's go to Judah. Thank you, and then we'll get back to Howling Lee and see if we can get past the streaming issues. So Judah, go ahead, please. 2 minutes.
Good morning.
Good morning. Sorry. Hang on. There we go. We see your slide, although I'm not hearing any audio. We're not hearing any audio. To restart.
All right. Can you hear me now?
Now I can hear you. Yeah, so you might want to
Okay. Yeah. Somebody muted me while I was unmuted. All right. This is an experiment we did for doing low-level coincident measurements of barium-140 on high-level systems with using gamma coincidence for the purpose of increasing sensitivity. This was in conjunction with our collaborators at AWE. The experiment was basically, we isolated barium-140 from HEU irradiation, and then we put it on Rasa filters and pucked it, and then did the counting on several systems. I won't go into the chemistry of how we did this. We measured it on several systems above ground and below ground, both with a singles system, so a single gamma and then a gamma. This was done both in the US and in the UK. We put it on at 0.07 and 0.15 becquerels because modeling had indicated that these were activity levels where a singles measurement would not be able to see the barium, but a coincidence system would. And we followed the typical station, particulate station, where it was collected for 24 hours, it was decayed for 24 hours, and then measured for 24 hours. The overall summary of what we saw was we were able to observe using a coincidence system that was not observable using a single system, which matched the modeling that the UK had done. The analysis of the coincidence data was analyzed via two methods, one method by the UK and one method by the US, and we had very similar results. So the overall end goal was met, where we were able to not just model, but also demonstrate that a coincidence system has higher sensitivity than a single system in a typical station operator mode. And all the data is in the poster, and please take a gander through and let me know if you have any questions.
Certainly, thank you. So we'll put Hao Ying on hold for one more minute. I see that Jacob Anderson has joined. So Jacob, if you are ready, you weren't here in the beginning, so we're not allowing any videos, but if you are ready, then you have the floor for 2 minutes. Thank you.
Okay, thank you. Good morning and good evening to everyone. I'm sorry, I need to share my screen. So I am
Still not seeing it. So there we go.
Okay, how about now? Okay, so I'm an infrasound scientist, and I'm here to convince you that by making infrasound sensors easier to deploy, cheaper, and smaller and lower power, that we can install more of them and collect better array data and make better inferences. Something like this happened in the related field of seismology over the last decade with the emergence of nodal sensors, and it very impressive inferences to be made about subsurface structures and seismic sources, and I hope that the same can be done with infrasound too, and I've been working on that with the GEM infrasound logger, and I'm here to present an application of that. So specifically, we were recording earthquake infrasound in mountainous areas. This is a good test of an infrasound array's resolving capability because basically these are very complex and dynamic wave fields where energy comes from several directions at once and the position of the wave field changes rapidly. A normal 3-element infrasound array is good for detecting the azimuth of a single wave propagating an array, but it would have a lot of trouble in a situation like this. So what I did was set up an array of 22 elements in about the same space that a normal 3-element array would take up. You see that the array response of this dense array is much more compact and gives it higher resolution. And if we look at these two bottom figures here showing the inferred azimuths of wave energy over time, and on the left use the full dense array, and on the right use a simple 3-element array, you can see that you get a lot more precision and detail when it's the full dense array. So basically, infrasound stations where energy comes from multiple directions at once, that's a common situation. And I believe that this method of installing denser arrays to get better resolution of the wave field is going to be broadly applicable. Thank you.
Thank you. Appreciate it. Let's go back to Hao Yang. So Hao Yang, do you want to try again?
Okay, can you hear me? Can you hear me?
Yes, I can hear you now. Yes.
Okay, I will share my screen.
Okay. The audio is much better.
Can you see my screen?
It's starting. Yes. Now I see a slide. Yes.
Okay. Hello, everyone. This is Lee from the joint team of HOPE and the Beijing Institute of Space Mechanics and Electricity, Beijing, China. My topic is analysis and design of wide spectral imaging spectrometer for CTBT OSI. Our spectrometer is aiming to satisfy the requirement of CTBT OSI, which needs compact structure, a wide spectrum range, and high SNR. According to the scenario of CTBT OSI, our spectrometer is designed with wide spectrum range from 400 to 5,000 nanometers, high GSD and high SNR, and a compact structure, small volume, and lightweight. The spectrometer includes the instrument and the integrated processor. With a special design of a mechanical interface, it could serve on the helicopters, even UAV. We choose oftener spectral structure with convex grating. The spectral part is 183 plus 191 plus 93 millimeters. Keystone and smile are better than 1/10 pixel, achieving high image quality. The spectrometer has finished the integration at ISNR reached down. This page shows the images shot by the spectrometer in our lab. Based on the further study and the comprehensive discussion with the experts in the field of nuclear test inspection, we expect to upgrade the spectrometer for better application. Thank you, everyone.
Thank you. Appreciate it.
Do you have an MXS? We don't know who is.
So there's a user logged on as MXS. Can you send a message to identify yourself?
I can send you a message for the name and post.
Then we also have Michael Swanwick. So Michael, if you're ready, we'll give you the floor for 2 minutes with no videos. Thank you.
Can you hear me?
Michael? Yes, I can hear you. Yes, it's good. And, oh, so you're an MXS.
I am. Sorry about that. That's my company initials. So we are developing.
I'm not seeing a slide. I hear the audio, but I don't see a slide.
Okay. I try to share.
Not yet. It says it's starting to share, but it's not streaming yet.
Okay. If it doesn't come on in a second, I think I will. We'll just go ahead without it. But
oh, there we go. It just came up.
okay.
I see it.
So I'm Michael Swanwick from a company called Creari in Hanover, New Hampshire in the US. We are developing an electrostatic precipitator for radionuclide particle collection as part of the next generation of RASA radionuclide aerosol sampler analyzer that was originally developed by P&L, and we're integrating into RASA 2.0, which will be more power efficient with much higher flow rates and the ability to sample at shorter time intervals. So we've done some previous work with the Department of Energy, and right now we are looking at a multi-strip design with multi-layers of Mylar that folds up and presents into a coincidence type detector. We should be able to do flow ranges at well over the CTBT requirements while still hitting the particle collection for 0.2 and 10 micron particles. We've done some initial breadboard subscale testing of this with very promising results. We've also done some analysis of what the form factor should look like in a coincidence detector, and that matched some of the Monte Carlo results from PNL. And right now we are designing and building a full-scale system to be tested in our lab. And I would also like to thank Ditcher for sponsoring this, and Ben Heshmet-Poor and Harry Miley at PNL, and Lance Liddy for their support, and all the other people at PNL. Thank you.
Thank you, appreciate it. And I see that there's a poster for Hemu Kafle. Hemu, are you online? Okay, I don't see Hemu. Maria Teresa Apolloner. Maria, are you online? Maria, no?
She used to work with us.
Valentin Gravarov. Valentin Gravarov? Online? No? Zazimov. Gleb Zazimov? No. And Erica Fencini. Erica Fencini online. And lastly, we have Mario Ruiz Romero. Mario, are you online? Sorry? Yes. Yes, so I think at this point we've gone through all the presentations, and we can open the floor for discussions and collaboration. So we have about 25 minutes. I'd like to see open the floor to any questions or other posters. You can raise your hand. Oh, all right. So we'll have Erica in a few minutes, it sounds like. So we would like you, if you have a question, you can enter it through the chat, and we can then raise the question. And in the meantime, I can ask Jacob. So Jacob, I'm interested in this idea about the low-cost sensors. So do you have any ideas as to what the actual cost would be for a low-cost sensor that would meet the sensitivity requirements that we use in the IMS for this dense array idea?
That's a good question. So I am not sure that it does meet the sensitivity requirements for operational use in the IMS. I am using it as a research grade tool, and perhaps the IMS would find it as useful as a research grade tool also, but maybe not for permanent monitoring.
So
I am aiming for a cost about 1,000.
Oh, okay. It's a diaphragm-based sensor, or is it solid state, or?
It's a MEMS-based sensor, and
Right.
it's integrated with a data logger with the objective of being able to reduce costs and speed of installation times. And the target price is $1,000 per unit. We're not there yet, but several groups have bought them for $1,200 per unit so far.
Okay, thank you. Yeah, interesting. I understand that Erica Fencini now online. Erica, are you online? Erica Fencini? Can we give you the floor for 2 minutes? No?
She's muted.
We have LinkedIn.
Yes, hello.
Oh,
Good
there we
afternoon,
go.
everybody. Sorry for being late.
So I can hear the audio, yes? You can share your screen for 2 minutes?
Okay, thank you. The machine is very late. Very slow, sorry.
Yes, we hear audio, but there's no,
Okay, I'm trying to find that.
it's here, yeah. Thank you.
Can you see them?
No, we hear audio, so the sharing doesn't seem to be working, video.
I'll be very quick.
So I think you can just go ahead and give us an audio 2 minutes.
Okay. Okay. So I have two presentations. The first one is automatic weather station. This one is actually is commonly used commercial available weather station, and it has been widely used in China in many areas, and we are trying to provide this equipment to CTBTO IMS and also on-site inspection. And we all know that for on-site inspection is very critical for getting the accurate and time weather data for supporting the sampling as well as the selection of the base of operations. And can you hear me?
Yes.
Okay. The second one is actually we call it full mode GNSS solution to ISI. We are trying to provide what we are trying to provide is we call it full mode. It means that we will integrate the GPS, GLONASS, Chinese Beidou, and European Galileo inside. It could be a terminal for positioning and navigation. And this would be our idea is to keep the balance of the political matter concerns as well as technical solution. As we all know, under the United Nations flag, there will be 4 main providers for navigation and positioning. That would be the 4 system providers. So in that case, it's something from that point of view. Okay, thank you.
Thank you.
The CPU is burning.
Erica, I see Erica Fencini is online. Erica, are you able to give your presentation?
Good
for 2
morning.
minutes?
Yes, sorry for the delay.
I can hear you.
Yes, perfect. Thank you very much. Now I'm sharing, and I also let me know if you see the screen.
Yes, now I see the screen.
Perfect. So really sorry again. Today, I really want to describe you this multi-particle detection device that was meant for the characterization of large sample air filters. The characteristics are the compactness, the active background reduction system provided by a veto outside that can be also placed inside the detector, the versatility, the real-time digital path analysis, and based on a fast electronics and the analysis software that performs online the analysis of the count rate. The system is made of a bottom layer of zinc sulfide for the detection of alpha and beta particles, a central larger crystal of cesium iodide. Sorry, I don't know what's happening, but oh my God. Cesium iodide for the gammas, and a plastic veto a plastic scintillator used as a veto. That is placed on top, and you see on the top picture. We tested this system at the INEA primary laboratory in Italy with the same procedure, with the same large sources that are used for normal contaminators that, of course, are smaller compared to the active area of this system. So we made it in 3 different configurations, so the central one and the 2 lateral ones. Just to let you know that the 2 lateral ones, since the sources were just placed close one to the other, they were the active area of the source was reduced because of the different dimension of the detector. So the plot here, I want to spend a little bit more time here. So the plot represents the efficiency of the system that we had with these different sources. Alpha on the top left, beta in the central one, and the gamma for the top right. As expected, the efficiency obtained with the source in central position are higher compared to the lateral ones, but they are not normalized by the real source emission area seen by the correspondent detector. That's the thing that I was saying.
Yeah, you're have your time. Could you wrap up in a few seconds, please?
Finished. The beta plot and the energy, the beta plot is more or less expected all for the full energy range. And I mean, that's all, because I know that the time is running.
Thank you.
Because of great. Sorry.
Thank you. Appreciate it. There's a question. Yes. So I believe we've been to all the presenters that were online. There's a question for Jim Hayes. We're not muted, no? Okay, so Jim, if you're able to field this question, were my eyes playing tricks on me, or did I notice a diagonal line in the Xenon 127 coincidence spectra collected with the XI system, similar to what would be seen with a cesium source? Jim, oh, maybe he left. Yeah, Jim, are you able to? So he might have left. Yeah, so that's fine. So since I've already asked an
Has no audio.
Yeah. Yeah. All right, we can. What's that?
As the famous D3K115 is now learning again.
Oh.
Oh no, he said that folks in
D3K, yes.
Yeah, so
Michael Fox could perhaps field this question about the diagonal line in the Xenon 127.
Yeah, so the Xenon 127 has a lot of different signals in there from the branching ratios of the different decay scheme, but there is going to be some of the diagonal line that you get from the Compton from the gamma ray as well. You can see that in other isotopes like the 131M or 133M. If you have a hot enough spike as well, you'll see the Compton scatter.
Thank you. And I see a question online. Not here. Oh, so that's a chat question. So I see another question for Michael, which I presume you can see. Does the improvement in electron resolution mean the silicon detector is more sensitive to metastable isotopes, given the efficiency is assumably lower than the plastic scintillator?
Yeah, so I think that is still the case. Is the sensitivity will be improved, especially when there's the ground state behind it. So it can improve. It has a smaller region of interest for the conversion electron peaks, and then there's less of an impact from the ground state 133. But the efficiency is going to be lower than the plastic, but we're working on methods to improve that as much as possible as well.
Thank you. I had a question for Clement about his wind noise reduction system. So it wasn't clear to me. Clement, you're still online?
Yep.
Yes. Yeah. So what is the primary physical characteristics of this wind noise reduction system? I mean, you know, we have the pipe arrays that are now gone down to a smaller size. Is this what's the fundamental physical difference between the existing wind noise reduction systems?
So over the last 10-20 years, we've been, as you say, deploying a standardized 18-meter system within the IMS network. And so we mainly provide two kinds of wind noise reduction system. One is in full stainless steel, and the other one is in flexible housing. These two reduction systems are very similar, depending on the way you install it. I mean, what is present, what my my presentation focus on is the need for this wind noise reduction system to be fully sealed, because we've done some simulation with MB3G connected to a wind noise reduction system, and we try to apply several kind of leaks, and the bigger the leak is, the less your wind noise reduction system is efficient. And we've got, you can go and see on my poster a slide stating that, different kind of leak simulation, and you can easily see that, in the region of interest, wind noise reduction system apply on an attenuation of 20 dB. If you got some big leaks on your wind noise reduction system, then this attenuation is like very less efficient, and your wind noise reduction system is working very less. And basically that's what my my presentation focus on. Also, and this is why you need, when you an installation of wind noise reduction system, to make sure your system is properly installed, and this is a big interest of doing some pressure testing.
Okay, thank you. That's very useful. So we only have about 4 minutes left, but I want to make sure that that Hemu Kafle, did you join us? I asked earlier, I didn't see you online. So do we have Hemu Kafle from Nepal? No? All right. Well, we only have a couple of minutes left. So any other questions to be posted for the conveners, for the participants? All right. Well, thank you so much. I'm not seeing any additional questions, and you can obviously all collaborate and connect with each other through the roster that was listed for the participants. I want to thank you very much. This is very useful to help us in the IMS move forward with technology improvements, and I look forward to speaking with some of you moving forward in the future. So again, thank you very much for attending this e-poster, and please enjoy the rest of the conference. Thank you.